Hi, everybody. We are back. In this segment, we're going to follow up on an idea that we had concluded with in the last segment on regularization, which was this notion of trying to restrict ourselves in terms of not structuring an overly complicated model in terms of having too many parameters, where we cause this problem known as overfitting. And regularization was the solution to the overfitting problem. It had us put on the brakes in terms of model complexity. So the tendency that we were thinking about in the last video was for people to generally want to throw in as many variables on the right-hand side of their regression as possible, meaning they are dramatically increasing the number of parameters that are needed to be estimated by including all of these X variables on the right-hand side. And we note that when we have very high levels of complexity, this starts to drive our out-of-sample prediction error up, okay, even though our in-sample error is getting lower, right? We reduce the bias, but we wind up causing more variance in our model. We increase that generalization error with excessive complexity. So regularization was the solution to this problem. It told us, hey, we need to put on the brakes. We need to move back in this direction in terms of model complexity. But we don't really know how far to move. We can move a little bit of regularization, or we can move a whole lot and wind up really underfitting. But you'll notice there's some optimal parameter here, K star, that actually minimizes our out-of-sample prediction error, right? It puts us right at the minimum of our out-of-sample prediction function right here. Okay, and that K value, that value K star there, that is really what we want to find. Okay, because that value will tell us essentially how much regularization to implement, right? And validation, this process known as validation, is actually going to help us find that by estimating our out-of-sample error, which is kind of an interesting thing to talk about. We've discussed this catch-22 in that we typically cannot observe the out-of-sample error, right? The out-of-sample error is the error on data points that we didn't sample from the population, relative to the data generating process here. And validation is a technique we're going to use to provide an estimate of what our out-of-sample error actually is. And the trick here, and it's not too complex of a trick once you think about it, but the trick is, and I'm going to go back to this analogy of giving you a practice exam and then giving you the same exam, right? If I give you a practice test and you train yourself on that data on that practice test, and then we use that same practice test to evaluate how good you are, right? Your prediction power, or your predictive power rather. Your performance is going to be really, really good because we're testing you on the same set that we trained you on. Okay, if we wanted to get a better, more honest measurement of how much you learned from that practice test, a better idea would be to give you a different test, right? Same concepts, but different data set, right? Generated from that same process, like same information, but different content, different exam. And that would give us a more honest assessment of your actual performance. So that's going to be the idea behind validation, is rather than building the entire model or building the model with all of the data, with the entire data set, okay, what we're going to do when we validate is we're actually going to hide some data from ourselves. We're going to hide a little bit of data, and we're going to build the model with the rest of it. And then we'll use the data that we've hidden from the model to actually test the efficacy of the predictions in the model here. All right, so that is the idea. We don't want to memorize all of the data. We'll memorize some of it, the training data. Okay, but then we'll test ourselves on data that we haven't memorized, that we haven't given the model to sort of see, right? We're not going to use that data to estimate the model. So let's talk about this notion of validation a little bit more, and specifically how it is related to regularization, to this idea that we need to restrict ourselves. Okay, so regularization, we need to restrict ourselves. We need to put on the brakes. Okay, validation is going to tell us when to really hit the brakes, when to stop. Okay, so when we looked at regularization, we showed that the way we augmented our cost function, so hopefully you remember from the last video that we had defined this thing called the augmented cost function, C, which depended on beta, and then we put a little tilde above it to denote that it was different than our regular cost function. Okay, but the augmented cost function was different in that we had some overfit penalty. And you might remember in the case of the ridge regression, that overfit penalty was the product of those two beta vectors, beta transpose beta, okay, which was the ridge regression penalty term that we used here. And there was also a lambda over n factor out in front of it, where lambda was a parameter that told us or forced how much of a trade-off we faced with that overfit penalty when we engaged in this process of cost minimization to estimate our parameters. So regularization, again, provided really a proxy for that generalization error omega, right? That's what this thing is here. That's what this overfit penalty, this quantity here is. It was a proxy for omega, which is really an unobservable, but we're trying to do a little bit better. Okay, now validation doesn't really help us estimate the quantity that regularization estimates. What validation does is it directly provides us a way of estimating the out of sample error on the left-hand side here. Okay, so that is how these two things are related. Right, regularization provide this overfit penalty trade-off to kind of capture that generalization error, right, from overly complex model. But validation allows us to estimate the out-of-sample error so we can get a more honest idea of how our model performs. Remember, the in-sample error, okay, E in, if we only use that as our criteria, that's like looking at the R squared, right, of the regression. How good is the fit of the model to the data? Okay, well, we don't care so much about how good we fit the data. We want to make sure that we're predicting against the data generating process well, the out-of-sample error related to the other observations in the population. So let's talk about how we're going to go ahead and engage in this process of validation. Okay, as I mentioned earlier, and let me explain this flow diagram here a little bit. So we're going to start off with our whole data set. So we'll just call this data set D here in this picture. Okay, this is the entire data set. And what we're going to do is we're going to break that data set into two parts. We're going to break it into a training, what we call partition, and a validation partition, a training set and a validation set. Sometimes they'll call the validation set a test set, but we'll actually see we can differentiate between validations and test sets momentarily. So this is the idea. If we started with n observations in our data set, we started with n observations. Okay, what we're going to do is we're going to hide k of them from ourselves. Okay, so the validation set is going to be the hidden data, and we're not going to use that data to build the model. We're not going to use that data to estimate the beta parameters. Okay, however, all the remaining observations, the remaining n minus k observations, those will remain in the training data set. Okay, so the training data set, that is the data set that is going to be used to build our model. Okay, training data set is going to be used to build the model. Right, and the validation set, okay, that is not going to be used to build the model. That is going to be used to help us test or calibrate the model. And that's what we're doing here. All right, now, the way this is going to work is the following. If we were to use the entire data set, okay, if we use the whole data set and we build our best model, given our hypothesis set, we're going to get some guess, right? Some optimal hypothesis G. That is our best guess at what that data generating process is. However, when we use the training data, you'll note the training data, we have lost a little bit of information because we've held out some observations. right? And we know that when we do that on the learning curve, a little farther to the left in terms of number of observations. So even if we use the same type of model, let's say we use a model with an intercept and 2x variables, same 2x variables, but now with the training subset instead of the entire data set, the optimal hypothesis that we're going to estimate there when we solve our cost minimization problem is not exactly the same as the hypothesis that we would get using the full set of observations. So G and G minus here, they're not exactly the same estimated set of parameters for the model. It might be the same model, intercept an x1 and an x2. Okay, but beta 0, beta 1, and beta 2 would be different for G in comparison to those values of beta 0, beta 1, and beta 2 that are optimally estimated under G minus. So the idea here is in order to figure out our out of sample error, okay, what we're going to do is we're going to compute an error metric, a prediction measure, okay, like the root mean square error, or the sum of the square residuals, or the mean square error, but we're going to do it only using the restricted hypothesis that we got by using the smaller data set here, the training data set, as opposed to the entire data set. All right, so let me just show you a little flow chart on the right here that kind of represents this breakdown. All right, so here's what's happening. We are starting over here. That's our whole data set, KD. Let me use a different color than yellow. That doesn't show well. So here's our whole data set. Okay, we're going to break that data set up into the training and into the validation sets. And we're not actually going to, we're not going to use this branch here. That branch, what that represents is if we had started with the whole data set and then we made our best guess at the hypothesis using the whole data set, but problem there is we don't have any holdout data to give us an honest estimate of our performance. We've memorized all of it. So we're not going to go down that branch anymore for implementing validation. Rather, we're going over here. We're breaking up the data into a training partition and a validation partition. And then we're going to use that training partition to figure out our optimal hypothesis on the training data. Gee, what is the best set of parameter estimates? And then what we're going to do is we're going to take that hypothesis and we are going to test it using the validation set. And that will give us a measure of our out of sample error that's a little bit more honest than testing the data, or testing the model rather, on the exact same set of data you used to train it. Okay, so that is the process of validation. Moving along. So the idea here is the following. We're going to use validation sets to really compare different models. Okay, we can train them with the training data, but then we'll run the model against the test data to see which model is the best out of sample. So now this picture gets a little bit more complicated. Let's suppose we have here M different models generated from a set of M different hypotheses. So each of those hypotheses, H1, H2, H3, HM, they're a different model. Maybe H1 is a simple linear hypothesis with the intercept and the slope. H2 is that hypothesis, but with another logged term or something, right? Everyone is a little bit different type of hypotheses here. So we have these different hypothesis sets, and we're going to use the training data to learn what the best hypothesis is for every single one of these different models that we could be looking at here. Okay? And then what we're going to do is we're going to take each of those optimally calibrated hypotheses from each of those possible hypothesis sets, and we are going to evaluate them, okay, against the validation set. So we have all these different models, okay, that we built from the training data, and we have the optimal parameters for each of those different models, right? So we have all these different optimal hypotheses, and we want to know which one's the best. And the way we're going to do that is by running them all against the validation data, okay, that holdout data. And whichever model performs the best out of sample, that is the model that we are going to pick. Okay, the one with the smallest validation error, okay, on that holdout data. So here is another flow diagram here kind of showing how this process works. All right, so this is a slightly bigger diagram than where we started before. So recall where we started before. Okay, we had our data. We took the data and we broke it up. Validation set, training set. Okay, now we are going to evaluate the training data on every single model that we are considering, all these different hypotheses. And each hypothesis gives us some optimal set of parameter estimates when we run our learning algorithm, like cost minimization. We run that algorithm that solves cost minimization. We get the optimal parameters for every single one of these possible hypotheses. Okay, and then what we're going to do is we are going to assess each of those optimal hypotheses against the validation set. And that will generate for us these out of sample error measures. So again, we had the validation data here. Okay, what are we doing? Well, we're passing the hypotheses that we estimated from each different hypothesis set, right? All these are different models. Okay, but we're testing them to generate these out of sample error estimates as a way for us to compare which model performs the best against the population data that we didn't use to build the model here. That gives us our out of sample error metric. Then we will choose our optimal hypothesis, and that defines the end model that we wind up with here. Okay, so that's the idea. Now, probably have a lot of questions at this point, like, how much data do I need to hold out to do this? The more data I hold out, the more sampling error I am subject to, and the more standard error we're going to have in our parameter estimates. And that's true. So there's a trade-off here. If you increase the size of that validation set, right, the larger validation set does give you a better estimate opportunity for that out of sample error, but it does reduce the integrity of the training data. You lose some degrees of freedom in your training data. There's not really a technical rule for how to split the validation sets from the training sets, but there are two typical standards that are used in industry. One says you should choose the size of the validation set by essentially taking the number of observations and dividing them by 5, which means you're partitioning the data set into 80% training and 20% validation. Okay, another industry standard that we've seen is slightly different. It says let's divide it 70-30. Okay, so 70% is used to train the model, 30% is used to validate or test, and I've given that option here. So it is possible now that we use the validation sets. If we're using the validation sets to make decisions now, we've kind of introduced another problem, and that is if we're using the validation sets to choose the model, then we've snooped a little bit. We've memorized a little bit more than we should have. Okay, and we're going to talk about this idea of data contamination. The test set, when we're trying to get the most honest assessment of our out-of-sample performance, that is what we want to be the least contaminated data set. Okay, so this test set, least contaminated. Validation sets, if they're used for decision making, they're a little bit more contaminated because we do use them to choose the best model. So they're used in decision making here. Okay, and the most contaminated part of the data is definitely that training data. That is the most contaminated data because we use that to actually build the model and estimate those parameters. Okay, validation sets are sometimes used to fine-tune some model parameters, but not estimate them all. Okay, but the test set is supposed to be a completely unadulterated or unsnooped data set that we didn't use for any model building and we didn't use for any model selection. So it may be the case that you actually have 3 different partitions. Okay, 70% goes to data, goes to the training data, but then we could split the remaining 30, 50-50 between a validation set, which we'll use to tweak our model or to choose the model. And then once we have our best model and we have to get an unbiased estimate of our out of sample error, or at least the most honest estimate here, then we'll go ahead and use the testing partition. So that mix here, okay, which is fairly standard in industry, is we'll use a 70-15-15 mix. 70% of the observations are used to train, 15% are used to validate. And then once we have our best model and we want to get an honest assessment of the out of sample error, the remaining 15% is totally unadulterated holdout data. And that is what we call the test set. So I want to be clear about this concept. The validation sets, they are used for learning. Okay, that validation data in that flow chart we looked at, that is used for making choices across different hypotheses that we've proposed. So if an estimate of E out causes us to learn something, then that data set is no longer a test set. It's a validation set because we're using still some of that information to tweak our model selection criteria. Now, as I mentioned before, the training set is the most contaminated data set. Okay, most contaminated. We use that to estimate all the model parameters. Okay, validation, though, is slightly contaminated. Given our beta parameters, we maybe use validation to figure out, well, what's the optimal lambda? What's the amount to regularize and figuring out those beta parameters? All right, so if we're using validation to regularize, that means we're using validation to learn and choose the right model, right? How much regularization do we need to restrict our hypotheses? Okay, and once we get that best hypothesis set, then we go ahead and we can test that against the totally clean test set, which was completely hidden from the model. We didn't use it at any stage, not to train, not to validate, and that'll give us our best assessment, right? Our least optimistic assessment of our prediction error, really the most honest assessment we can get here. There are other methods of validation. There's a technique that's pretty interesting known as the jackknife estimator, or as some of my British friends like to call it, the LOO, the leave one out estimator. And this technique applies something more generally referred to as cross-validation, whereby you might think that, well, if we validate using one particular data set, there's some sampling error relative to that data set. So what would maybe be more interesting to think about is by breaking up your data set into many different validation sets, computing the errors on all of them, and then averaging that error together to give you some sort of an average validation error across all the possible validation sets that you could have sampled here. So this idea of cross-validation, what that does is it applies multiple validation sets to help make model decisions and to mitigate this problem of memorization within a particular validation set. We might get really good on that one validation set, but then if we switch to a different one, we'll get a more honest estimate of our out of sample error. So the way the jackknife estimator works is the following. Imagine taking your data set and we use every observation except for one. We use n-1 observations to train the data. Okay, and then what we're going to do here is we're going to take this one observation that we left out, and we're going to calculate our prediction error on just that one observation. Okay, so we have an error measure on 1 point, and then we're going to do this whole process again. We take n-1 different points, build a model with those, and we take a different holdout point, and we calculate the error on that particular holdout point. Okay, so imagine we keep doing that over and over such that we have now n different errors that we've computed by using every single data point as a holdout data point in one of n different models that we've built this way. So we're going to build n different models. Each model, okay, we hold out one data point, we build the model with the rest of them as the training data, and then we keep doing this over and over again, looping through all n observations in the data set. And then we're going to take the average of all n of those error terms. Okay, so we're running the estimated model on that holdout point for one particular set of parameters, and then we're looping this process over every single data point, okay, to generate an average out of sample error here. So we're averaging the out of sample error here across these n models, And this results in slightly more data contamination in the validation sets since they're also being used to help form parameter estimates here. But at the same point, we can be a little bit more confident that the validation error we're computing here, our estimate of E out, okay, is not super sensitive to the particular observations that we had sampled or set aside for this process of validation. So in terms of using cross-validation here, the hypothesis is learned from the training set, right? So that the single observation is not contaminated relative to that particular hypothesis, right? That single observation we held out, didn't see that, okay, when we built the model. And the cross-validation error here averages that validation error on a single holdout observation across all possible variants of the hypothesis we estimate, right? Across all the different B parameters we could get from every training set corresponding to a particular holdout observation. So the final hypothesis here that we're going to learn, right, that, GN minus here, our final hypothesis, okay, the way we're going to calculate that error is by averaging these individual cross-validation errors, these EN terms, which is the validation error that we're computing here using every one of those N data sets where we've held out one observation, we've trained it with the N minus one other observation. So I'm going to show you here an example of this that I hope will make this a little bit clearer. But let's suppose we had a linear model where we have to choose an intercept and a slope. Let's say we have just one X and one Y variable here. Okay, so I want you to look just at the top set of diagrams for the moment. Here is a linear model up top. Okay, and suppose we have 3 data points. So here is how the Lou estimator, or the jackknife estimator, works. In this first panel, okay, what we're going to do here is build the model using only these 2 data points. And it should make sense that the model that we're going to build only using those 2 data points should just go right through those 2 data points, right? Fits them perfectly in sample. But you'll notice the data point we didn't use to build that model, we have some error, and we can measure that distance here, E1. That is the validation error on that first data point. Okay, then what do? Well, we use a new data set. We do the same thing. So in the second panel here, we use these 2 data points to build the model. Okay, but we leave out this middle data point here now, and we use that to test the model by measuring that vertical distance, that validation error on data point number 2. Last but not least, we use the first 2 data points to build the model. Okay, so we get, again, a nice best linear hypothesis on these 2 data points to minimize the in-sample error. It goes right through those 2 data points. But now you'll notice we have some error on E3 here, on that third data point. Okay, and the way we would compute the cross-validation error is by just adding up those individual errors, E1, E2, and E3, and then taking the average. Okay, so that's what we're doing down here. That would be our cross-validation error. Okay, the bottom panel shows essentially the same idea. Okay, but if you had just a constant hypothesis, so if we had these 2 data points, best constant hypothesis is the average line that goes right between the Y values. So there's some error on that first data point. We do the same thing here, error on the second, error on the third. And again, we can compute that cross-validation error by looking at the average of the errors on each one of those holdout data points. So this is a kind of an extreme case of cross-validation where we would have N different possible partitionings or N different combinations of how we're splitting up the training and the test sets. Okay, where each one, we have one holdout data point, and then we have N minus 1 data points that we use to train. All right, so I just want to show you a picture of cross-validation in action here with some regularization. So we talked about this digits classification task. Again, borrowing some of these diagrams from a colleague, Dr. Yasir Abu Mustafa over at Caltech, who teaches a wonderful course called Learning from Data. Highly recommend you take it. Little plug for him there. But this digits classification task we talked about needing really only two features that were transformations of other inputs. We looked at the symmetry of the digit as well as the average intensity. And here we're looking at a specific classification task. And that classification task involves us deciding if the digit we're looking at is 1 or not 1. Okay, so you remember the number 1, it's symmetric, high symmetry, but it doesn't take up a lot of space when you write the digit 1. So it's low intensity, high symmetry, which is why we're getting a lot of positive observations up here in the top left that we're classifying as 1s. And then we have a lot of negative observations, not 1s, down here in the bottom right. Okay, but you'll notice there are some exceptions. There's a couple blue dots that kind of move down into the bottom right region, and there are some red dots up here in the top left region. And what we're going to look at is the process of using cross-validation and regularizing to help us optimally choose a model. Okay, and we start off here with a very, very simple model, okay, where our right-hand regressors, we have a constant, an x1 and an x2, so that means we have 3 parameter estimates to look at here, right? If this was regression, that means we have a beta 0, a beta 1, and a beta 2 to estimate. And what I want you to think about now is the process of adding more variables, checking the in-sample error, the cross-validation error, and the out-of-sample error on the training sets, the validation sets, and the test sets respectively. And then we're going to do that over and over and over as we add more and more features to our model until we have a very, very, very complicated and high dimensional feature set. Not just one x1 and x2 here, but we also have quadratic transformations with interactions, cubic transformations with interactions, so on and so forth, all the way up to what looks like a 5th order polynomial. Okay, point being, as we increase the complexity of the model, we're increasing the number of betas we need to estimate by adding all these extra features. So if we plotted here the estimated values of the in-sample error, the out-of-sample error, and the validation error, we see some interesting results that we should expect. Note that as the number of features goes up along that horizontal axis here, right? Number of features is increasing. That's the number of betas we have to estimate goes up, meaning our model complexity is increasing. You should see that, not to much surprise, our in-sample fit gets better and better, and that our in-sample error gets driven down towards 0. Okay, however, you'll notice our out-of-sample error goes down a little bit, but at some level of complexity, it starts to skyrocket, starts to jump up. Okay, and we want to identify really the minimum of that out-of-sample error. That's really ideally what we want to do here. Okay, we want to figure out the minimum, which looks to be about right here at around 5 features used. So that would define our optimal model complexity in this case. Let's use a gentle line for that. That's our optimal model complexity. It looks right about here, right, which puts us at the minimum of our E out. And again, we only really use the E out not to make decisions, but just to give ourselves some idea of how well we're performing. Okay, the most honest estimate of our performance. So the important thing to see here that we do use to make decisions is the validation set. And that validation set, hey, what does that do? Well, it does track E out pretty closely. Okay, notice it dips down at first, reaches a minimum, and then comes back up. Okay, so the thing I want you to see here is that that cross-validation error, ECV, that does track E out pretty well. Right? Note that they both more or less reach a minimum value right around 5 features being used here. So 5 would be our optimal complexity of the model. That's where we want to put on the brakes in terms of not overfitting versus not underfitting. If I go less than 5 features, then we wind up underfitting a little bit here. So that's the key idea. Okay, note that the CV is a little bit lower. The cross-validation error is a little bit lower than E out, as we also suspect, because we're using that validation set to make model decisions, which means it's not quite giving us as honest of an estimate of our out of sample performance, right? Our actual out of sample error is a little higher because using those cross validation sets, we're a little bit better than we think we are because we've snooped the data in those sets. We've contaminated the sets a little bit here. Okay, so just a couple results here without using validation. Okay, here is what the hypothesis set looked like. Okay, it was kind of complicated. You'll notice it's got some holes in it, some nonlinearities, and we have a real curvy surface here that we're looking at, right? Real curvy surface, nonlinear relationships. Okay, in that barrier that defines the positive region from the negative region. And you can see here with a very complex relationship, one good thing that happened is we drove that in-sample error down to 0. Able to drive that thing down to 0. Okay, but our out-of-sample error was up at 2.5% on the test set. Okay, but when we used validation, we restrict ourselves. We optimally choose our model using this process of validation. Okay, then you can see here, there's a little bit of trade-off, right? E in goes up a little bit, up to 0.8%, but we get a nice reduction in our out-of-sample error down to 1.5%. Okay, so validation, that's a good thing we want to do. All right, fitting the data is one thing, regularize is another, but if you want to be really good at machine learning and model selection, validation is absolutely a must. I want to wrap up by talking about this idea of multifold cross-validation. And we've already seen the most extreme case of this. The jackknife for the Liu estimator is the most extreme case of multifold cross-validation where we've divided the data up so much, right? It's really fine. We're using one point as a holdout point, as a test set, or validation set rather. So this is not as extreme of a case here, but imagine breaking the data set up into K validation sets. And for each validation set, we're going to use the remaining K-1 sets to train the data, and then we'll measure our validation error on that one holdout validation set. Okay, and if we were to think about this idea in the context of tenfold cross-validation, then what we're going to do here is we're going to take our data set and we're going to break it all up into 10 different partitions. We'll pick one partition here, D4, to validate the data, and then we're going to use all the other partitions that are not D4. We're going to use all of those to actually train the model. So we use D1, D2, D3, D5, D6, D7, D8, D9, D10. We use all those observations to estimate the parameters of the model. And then we're going to test, okay, that model on D4 to get our validation error. Then we'll do the same thing by cycling through which data set is our validation set. Maybe next we choose, let's say D5 as the validation set. And then every other data set that's not D5 is used to train. Okay, and then we use D5 to calculate a validation error, so on and so forth, such that by the end of the process, we'll have 10 different validation errors. We can look at the average across those 10, much like we did with the jackknife estimator. So just to be clear, this is a less extreme version of that jackknife estimator, of that Liu estimator. And the Liu estimator is essentially, in this context, we would call this n-fold cross-validation. So this is, again, another more complex way to think about validation, not too extreme as the Liu estimator, this jackknife estimator, but it's kind of a medium in between using only one validation partition and using every single data point as a validation partition. So that wraps up our discussion of validation, cross-validation, and model selection. If you're really interested in getting good at prediction, who cares about your in-sample error? It's always easy to drive that to 0 by making the model more complex. But we want to know really, in terms of predicting well, how well do we do against the population function, against that data generating function? And validation, right, hiding some of that data from ourselves, allow us to get a much more honest assessment of our performance against the data generating process itself. So we'll see you next time.